you will cooperate. Thank you. All right. So real quick, before we do this, if you look at this here, this is going to explain a little bit. Somebody had a good question in the office hours about how do I know that there exists a power series solution? And there's a theorem down here about the existence of power series solutions. So that's down there if you want to look at it. Analytic is actually defined in section 6.1. So all it means to be analytic at a point is that a power series for that function exists at that point, or about that point. So, stuff like e to the x, cosine x, sine x, all those kind of things, they have power series representations around any point. So for any given dE, so for this one, this is second order. This is what we're looking at currently. As long as P of x and Q of x are analytic at x equal x naught, P of x and Q of x are analytic, meaning that whatever functions are here, a power series exists at that point. Right? You can write a power series around that x naught. So, for example, looking at so that would mean it would be an ordinary point. X naught would be an ordinary point. If it's not an ordinary point, then it's what's called a singular point. And then there's two different kinds of singular points that are discussed in the next section, one of which is easier to find the answer to, but much harder than what we have to do to find these answers. So look at everybody's got this handout, right? The 6.2. So very quickly, can you identify, for each of these things, look at the very first differential equation there. What are P of x and Q of x? For that y double prime plus 6y prime minus 7y equals 0, that guy?
6 and negative 7?
Yeah, 6 and negative 7. So there's constant functions. You gotta love that. They are definitely analytic everywhere because I tell you the power series representation, ready? 6 and negative 7. Right, so they're analytic everywhere. So are there any singular points? No. And there's a little shortcut, a little note. Obviously, if you have polynomial coefficients, it's going to be a singular point if the thing in front of here, before you divide, if that is equal to 0 somewhere, then obviously that's going to be a location of a singular point. Because you're going to have, so for example, the second to last one, the x squared minus 4 one. Why can't I identify P of x and Q of x yet for that second to last dE?
It's not in the right form.
Not in the right form. You got to divide by x squared minus 4, and then P of x. What would P of x be for that one?
X over x squared minus 4.
X over x squared minus 4, and Q of x would be
1 over x squared.
negative 1 over x squared minus 4. And those are both not analytic where?
Plus or minus 2.
Plus or minus 2, so those would be singular points. Right? So I couldn't use the methods of this section if I wanted to find a solution around 2 or negative 2. I can use the methods of this section if they're ordinary points, if they're analytic at those points. Analytic, again, means a power series representation exists around that point. Yes?
So 2 and negative 2 are the singular points?
Yes, I love it. That very last one, you could argue, it's the same kind of thing except plus 4, right? So what would the singular points be?
Plus or minus 2, huh?
Yeah, but normally we're thinking about real stuff, but you certainly could do a lot of what we do in the complex plane also. So yeah, you could argue it's x equal plus or minus 2y, and if you don't care about complex numbers, then it's really no singular points in the area, in the region you're caring about. Does that make sense by itself? Is that cool? And then, the third, let's work our way back up. The third one, the x, y double prime. What's P of x? No?
Oh, fine.
1 over x, I love it. So you got to divide that x to see what P and Q are. What's Q of x then? So the only singular point would be x equals 0, because 1 over x, not analytic at 0. And then the second one is one of the more interesting things on here, but it still doesn't really lead anywhere, to be honest. What's p of x? And the second one? Cosine x and q of x, e to the x. And both of those are beautiful, right? Entirely too beautiful. So are there any singular points for those? No. What if, instead of cosine, what if I put secant x? Then there would be an infinite number of single points, right? Wherever secant goes to infinity, basically wherever cosine is 0. Okay, cool. So that kind of connects a little better the picture about when am I allowed to use these processes, right? When am I allowed to do what we did last time, which is assume this, throw it in, go to town. It needs to be trying to find a power series around an ordinary point, and the ordinary point is built off the ideas of analytic, and singular would be if it's not ordinary. And what else do I want to say about this? Oh, and then theorem 6.2.1, it fills in the idea of the existence. We always like to know, how do I know if a solution exists? Why would I even start this thing off? Okay. Can you guys look at the bottom of this page? So that's the radius of convergence is talking about right there, right? R, and they tell you R is the distance from x naught to the closest singular point. So that is the minimum value, the lower bound for the radius. Kind of makes sense that there very well could be a problem at a singular point, that it can't be a part of your interval of convergence, right? So that's why it's a minimum value for R. So, for example, if I have this dE, what are my, we talked about this one a second ago, what are my singular points for this? It almost doesn't matter, blah, blah, blah. What are the singular points? Yeah, there are 2 and negative 2, plus or minus 2. And it asks you, what if I were to do it around x equals 0? What would the minimum radius be?
2.
Yeah, the distance between the point you're doing it around, the ordinary point you're doing it around, and the closest singular point. So that would be minimum radius would then be 2. And what if I did it around x equals 1?
1.
The minimum radius would be 1.
So that's x naught, the when you're going around?
Yeah, exactly. These are the, if you want to put little x naughts on there. Like that's the thing I'm doing it around. It's x minus x
At
naught.
that point, right?
Say again?
Is center at that point?
Yes, I
X
love it.
naught?
So it's like the old x minus a.
Yeah.
Except now, every now and again, you'll see it as x minus x
This is
naught.
based on McLaren and Taylor series, right?
Yeah, that's the more
Yeah,
general
idea.
Taylor series. This would be, of course, Maclaurin. But again, Taylor did this too,
Yeah.
right? And then people go, well, why does Maclaurin get credit? Because again, they did it at the same time. So give them both props.
How do we determine what x naught is?
No, that has to be given to you.
Oh.
Yeah. Thank
Can you
God.
solve,
Right.
though?
They have to tell you, find a solution around this point. So then you say to yourself, okay, if it's a singular point, I can't do section 6.2. It's got to be an ordinary point to do 6.2. I like it. And your brain just starts going, well, all right, what's not ordinary? So many things are not ordinary now that I didn't know about before. Okay, so let's do this. So last class, I apologize. I didn't mean to make it seem as if you guys were going to have to, every problem, figure out the pattern and figure out what function. That was just me trying to take it a step further, to show you the connection between, we know how to get the solutions. If I do it this way, they better be the same damn solutions. The DEs we did had processes we had learned before to get nice sine, cosine, and all e to the x power and stuff. Unfortunately, when you do power series stuff, the pattern can be very muddled, and we saw that. So that was, I didn't mean to make it seem as if every problem was going to involve trying to tease out a pattern from something. Oh my God, no, it's not. In fact, most of the answers you're going to get for 6.2 are going to be C0 equals this, C1 equals this, and then just writing C0 plus C1x plus C2, that just writing, just collecting all your all your values for C3, C4, C5. You're not going to have to then take it down and figure out what function it relates to. My God. All right, that is gross, like we saw last time. Not impossible, just gross. So let's look at this guy. Let's do this guy the way that you would need to do it for homework. This is actually number 9 in the homework section. I have no idea if I signed it or not. It doesn't matter. So try to get as far as you can with this. Oh, if I was you, I would just have these just kind of like written on a piece of paper somewhere because they are almost always the same. You can just shift it if it's got a different A or X naught that you're doing it around, right? I really, really hope that everyone can see past the series notation and realize it's just frickin' power rule definition. Because it's just a polynomial. This is all that is a polynomial. Sure, it goes forever. But derivatives of any polynomial, I don't care how long, are easy. Period. Get this started here a little bit. That's just bam, 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 bam. It's like emerald. Is that too old of a reference now? Is emerald still around? You guys know emerald?
Yes.
You still know? Before you start doing anything to these, what's one thing you got to take care of at this step right now? No. Before you start messing with that, what's not consolidated yet?
Put in the X's.
Yeah, the 2x should go in. Because then that'll tell you what you really have here. So then, that's in a sense, that's kind of nice. Because what's it going to do? It's going to fill this dude in. You can leave both of these guys alone. It's just this guy that's you know. Come on. Oh, wait a minute. So let's see. Minus, so then you get this. What do you get? 2n x to the n, because that is 1, fills that in. So these two are fine in terms of like terms. That's the first thing you worry about is like terms, because then you can just pull terms off to make the indices the same. So he needs a little bit of help.
So you don't worry about the n of the next term, or the 2n
Say it one more time.
in the middle one, where there's 2n.
Sure.
So
Yeah.
this case is not the same as the last one. This is
All right. So our Are 7y and 5y the same? No. Are they like terms? Yes. So what's like terms care about? The functional piece, right? The variable piece. The coefficient doesn't matter with shit, right? Does it make sense?
But there's no n at all. That's what I'm saying.
Yeah, who cares? There's no 7 at all here. But who cares? So even this, are these like terms? AY plus BY. Are those like terms? Yes. How do you add them?
H plus B times Y.
Yes. So that's what we did last time. Remember, we took that x to the n out and then just wrote all the coefficient stuff together. And that's where the recursion relation comes from. That's the only thing we are able to do. We can't get everything the same. There's no way. So we get to the x to the n's to the same, so they can just go to the side. And then I can focus all my attention on the coefficients. Yeah. And there's going to be some string, some expression involving n. Yeah.
Can you explain how you distributed that 2x?
Yeah, just multiplied it. So the 2 just goes in. And x times x to the n minus 1 is x to the n. Now
you
watch.
just added the-
Let me do this. Watch this. Help me out here.
HB times A to B.
Help me out here, real quick, just to show you some concrete stuff. Because I know there's more than just one of you guys that are wondering this. This is n equals 1 to infinity. Can you guys tell me the first few terms of this? C? 1, because that'd be 1 x to the 0. Plus 2c2 x plus 3c3 x squared. Alright, and of course you can see the idea captured. The power is always 1 behind those guys. All right, that's what that says, right? Now, what if I do this to it? Can I just distribute that in there, right? And actually, not even the negative. We just leave the negative in between the summations. So this will be 2c1x plus 4c2x squared. So what did that do to all the powers? They're all now
Decrease.
1 bigger because they gave everybody 1 more x. So that's what's behind the scenes, is this infinite polynomial, and then we're just distributing. But the same thing's going to happen in every term. They're all going to get 1 more x. So the thing that represents every single variable piece will now just go up by 1 in the power, because every single term is going to get 1 more x.
Okay.
That's all that's happening. That's the beauty. Series are fundamentally simple, unless you're doing weird shit like finding patterns and trying to connect it to something that's a little bit worse. But working algebraically with series has to be simple, because they're just adding stuff, right? They're just polynomials. So what do you have to do to this piece?
N plus 2.
Yeah, we have to shift it on the n axis, if you want to look at it like that. So n equals 0, n plus 2, n plus 1, n plus 2, x to the n. I like it. So whatever way you look at that, you can think about it, what would you make n? So this becomes n total. I would make n go to n plus 2. And that's why the book uses k, because it's sort of related to, officially you can't say, like in computer science, if you said n equals n plus 1, that's kind of a no-no, or go to 10, or something, if you've ever done any computer programming. But who really gives a shit? It's just a variable. I really always hated changing everything to k or something. That's just, to me, it was just kind of dumb. I know what I mean, so who cares? But in case in the future you hit somebody that doesn't see it that way, then just humor them. The same way you humor me, I'm sure. So now, is everything okay yet? On one level it's okay, right? It's okay on what level? Yeah, they're like terms, right? The variable pieces are like terms, but the indices on the summations don't match. So the summations themselves can't be expressed more concisely yet. So what do I have to do?
Take some terms out.
Yeah, which ones do I take terms out of?
First 2.
The lower ones, right? Because if I take the 0th term out, what's left starting at the first term. 0th term comes out, then what's left starts at the first term, and then they all start at the first term. Hey, then they really are completely ready to go together, right? So what's the first term here, the 0th value?
2C2.
Yeah, 2, C2, and then of course x to the 0. So now that'll be plus n equals 1 to infinity, all this business. Is it pretty cool with the fact that nothing inside changes when I do that? It's the same way like if I start making an xy table, just because I plug a 1 in, the function doesn't go, oh, I'm going to change. No, it's got to stay the same function that I'm working with, right? I'm working with this function of n. It stays the same. Just because I did one value, who cares? The middle is cool where it is. And then the last dude, if I take one term off,
C0.
C0 plus, yeah, cool, I like it. So, let's write what we got, and this sort of relates to what I was talking over here about earlier. Let's see what we got here. Are you able to get everything there, little camera dude? I don't know. What do we got? So we got, let me put out front the little pieces by themselves. 2C1 plus C0, right? Mm-hmm. And then let me make one big ass summation.
2C2.
2C2, thank you. Oh yeah, good writing, Jeff. So what do I have inside? I have this. Minus 2NCN plus CN with an x to the n at the end equals 0. Mm-hmm. What is the lowest degree inside there on the variable? The lowest degree? No, the lowest degree on the variable. 1. I like it. And out here, these are
0.
constants.
Yeah.
I like it. That's why I can do this next step. Sometimes students look at this next step a little incorrectly. I mean, so every constant thing has to add to be 0 because there are no constants over here. Right? Or the constant is 0, either way you look at it. Every x to the first has to add to be 0. Every x squared has to add to be 0. And that would be the recursion relation we'll set up. These guys kick so much ass. What's got to be true about 2C2 plus C0? Has equals 0. So that sets up a relationship. That tells me that C2 equals negative C0 over 2. So I already know a relationship between C2 and C0. And now if I set up a recursion, now what can I do? Let me kind of clean this up a little bit. So I got n plus 2, n plus 1, Cn plus 2. What can I do with this? Yeah, so that's going to be plus, 1 minus 2n Cn equals 0. So every coefficient of every, for every value of n, the coefficient of that x to the n has to be 0. Because there are no x to the first, x squared, x to the n's over there. It's just equating coefficients. And again, what drives the definition of a function in power series notation is the CNs. That's what makes it different. That's like the DNA of the freaking thing, right? If I change that, I change the thing, right? Genome stuff. All right. So then Cn plus 2 equals, do you see how you can just turn that around, right? Is that cool? 2n minus 1 Cn divided by n plus 2, n plus 1. That is what you are going for, is that recurrence relation. Why? Because the freaking CNs define the function. And what are you trying to get? The functional answer. That's what you're trying to get. So that's why it makes sense that that's where I want to get to. Now I can start and just messing with this thing. All right, what's the... So if I plug a 0 in, I'll get the relate. Now let's just verify this. If I plug a 0 in, we kind of know what should happen because we already know what C2 is related to. So let's just kind of verify. For n equals 0, why can't I do anything less than this? Because I don't have any C negative ones, because from the beginning, my assumption was it starts with C0, right? So just realize I'm not arbitrarily picking something. So n equals 0 would lead to what? C2 equals negative C0 over 2. Yay! I mean, that really feels good when you're like, well, yeah, all right, let me do that. Oh my God, I got the same shit I just got. But one level that's like, whoa, and another level you should realize, who cares? Of course it's that way. It has to be that way.
So
Now you guys,
Oh, so you can like pull out the C2 and the 2C2 and the C0.
why did we have to do that? Just to make the indices the same, right? So I could put these together.
Oh, I got you. Okay.
Yeah. But whatever relationship this is, has to kind of go along with what this says.
You mess up, you know, right?
Yeah, exactly. You'll say C2 is negative C, and then over here it says C2 equals 18 C0. Like, I did something wrong. Yes?
Going back to the starting at n equals 0, would there ever be a reason for you to start before that? Like, start with n equals
If you do something really interesting with your choice of changing n here, yes, there could be. But almost never if you don't. If you go to x to the n, it almost will never happen. Yeah. Notice how I still cover my ass. It almost will never happen.
Are there any like applications
Living by your shirt.
real world where people like use?
On that level, it's just, on that level, it would just be a computational choice. I mean, like, I love the number -1, so I make sure it shows up in there, you know.
Is arbitrary?
The relationships between things are what matters here. It doesn't matter if I start at n equal -48. It doesn't matter. The relationship between everything is what matters, and that's not going to change based on where I want to start at. Because if I change where I start, I change fundamentally the look of the stuff inside, so that it all kind of balances everything out. I like it. You guys keep going. Get the first 5 values of n, right? N equals 1, 2, 3, 4, 5. Is it okay if I take this away here, this part? Oh, some of you guys are like, yeah, please do. So this isn't, I mean, this, you know, compared to some of the stuff we've done, you're like, yeah, this is kick-ass, just plug the values of n, and it's awesome. So what do you get here? You get C3 equals what?
C1 over 6.
Yeah, C1 over 6, I like it. And then you get C4 equals,
C2 over 8.
yeah, so you'll get 3C2 over 8, over 12, right? Yeah, over 12, which is C2 over 4, which is negative C0 over 8. So when you're doing this, you only want C0 and C1 to show up for everybody. Why does that make sense? Because how many answers should there be to this second order DE. 2. So one answer will be controlled by the C0s, and one answer will be controlled by the C1s. That's kind of nice, to be honest. So this equals negative C0 over 8. Let's see, and keep going. What do you guess first? N equal 3.
C1 over 24.
Yeah, you'll get...
Something
Well, all right, let me catch up to you. For N equal 3, you'll get 5C3 over 5 times 4, 20. So C3 over 4, but what was C3?
C1.
C1 over 6, so I get C1 over 24.
Sorry.
Let's do maybe one more here. C6 now for N equal 4. So you get 7 C4 over 6 times 5, so over 30. And then C4 was negative C0 over 8. So you get negative 7 C4 over 240. That looks gross.
C0?
C0, yeah, thank you. All your own advice, Jeff. All right. If you did N equals 5, that's great for you. Let's forget that. So look over here. So really what I could do right now, this is the answer. We assume this is the form of the answer. And if you write it out, you start to see why we do what we do. If we can figure out what each of these things are, or at least based on 2 of them, then I get the answer. Right? So I get y equals C0 plus C1x. C2 was negative C0 over 2x squared. C3 is C1 over 6, so I get plus C1 over 6x cubed. C4 is negative C0 over 8, so minus C0 over 8x to the 4th. C5 is C1 over 24, so plus C1 over 24x to the 5th. And C6 was negative 7 C0 over 240 x to the 6th. Blah, blah, blah. So what's one solution by itself? The stuff that's controlled by C0, so it would be
C0
1
minus 1/2
minus x squared over 2
plus negative.
minus x to the 4th over 8 minus 7 over 240 x to the 6th, blah, 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 blah. And the other one is the one controlled by C1s. That would be x plus C1 over 6. X, no, get out of there, C1. X cubed over 6 plus x to the 5th over 24. That's all we did. Yay.
Just sine and cosine, right?
Yeah, it could be alternating with
I mean, the reason you think that is because the change in between these two, but it doesn't really
It could be an
match.
alternating function with negative 1 to the n.
So you could try to find a pattern there, but they don't ask you to. That's what I'm trying to tell you. The stuff I was doing last time was just me trying to be hopeful about connecting the DEs we had solved already with this new approach. They have to agree. Right? And I was just trying to, I was trying to create a problem where we knew the answer and I was hoping that it would come out nice, and it just, the relationship was grosser than I wanted it to be. Yeah.
So because you you found like the first couple terms there, and you found the recurrence relation, you essentially say like you can get as many terms as you want as long as you want to do that calculation.
Yes.
Okay.
And I mean, right now we could see if there's almost has to be a pattern here. You know, there has to be a pattern. You can't always see it very easily, but we could work a pattern out, which would. But to be honest, we already have a pattern in the most important part of the series, so you can just go out as far as you need to. So if you're doing this with a practical application, then you go out as far as you need to for tolerance, for how far off you can be, right? And sure, this might be a part of a software program you're using that sets up engineering stuff, whatever, but still, for the frickin' humans, we should understand what the shit's going on in there so that something freaky happens. We're like, oh, the math ain't jiving because I got this thing wrong. Boom, right? I remember this one guy in particular, he says, well, when I get a job, I'm going to have a sheet with all the shit on it. And I'm like, well, if you ain't got a job, you got to shut your mouth. Right? Plus, when you get a job, I'm hoping as the human, you understand more than the computer does. Right? Computer can do stuff quickly. We better understand stuff well.
We got the internet now, so I know that was not an answer at work.
Yeah, pretty much. Okay, does that make you feel a little bit better about 6.2? The process is the same. The assumptions here are the same. I don't think they make anything too freaky about. All right, yeah. I mean, the first couple talk about the minimum radius of convergence. So you do have to find the singular points. They don't tell you to create a power series around a point that's not ordinary. In fact, in the instructions, they always say around the ordinary point, blah, blah, blah. Okay. So how's that for 6.2? You guys want to do another one of those, or do you want to? I'm curious. All right. You'd hope I have learned my lesson, but let's see what happens here.
Make another one?
Yeah, but tell me this. What DEs have as their answers like x squared? And therefore their power series should have what happening? A bunch of constants should become zero, right?
Okay.
So I can't remember off the top of my head if any of these, it looks like no. We kind of stay away from that. But if I were you, I'd be a little curious how that work looks like. If the answer, so for example, can somebody construct a DE? This sounds like a problem I can give you on a test, like the final or something. Construct a DE where the answer is... I already asked you these kind of questions. I can't remember if it was just bonus or not. The answer is y equals c1 x squared plus c2, what you got, Jeff? X to the negative 2, sure. What kind of DE would that have to come from? Push over. I like it. Now, you have to be careful about how to figure out the coefficients for that Cauchy Euler to work correctly to get you here. Yes, m squared.
Plus 4. Because it'll have to be I, right?
Minus 4. It's B minus.
Minus 4, because otherwise you get complex solutions, in which case I would have had cosine and natural log of x running around. Right? But what's the form of... So here's what we're working towards, right? But how do these relate to the, in general, the auxiliary equation? Well, the auxiliary equation would look like what? Let's cut to the chase here. I know it's going to be 1 there. Is that cool? But maybe not. Let's leave that there for now. It'd be a m squared, b minus a, m, plus c. Right? And of course, this is a consequence of the fact that the derivatives are not as nice as e. It's going to be offset a little bit. So now a is 1. Let's go ahead and make that adjustment here. A is 1. I know this has to be 0, right? So a is 1. I know this has to be 0, so B has to be 1. And then that means that C has to be -4. Okay, so let's write down. Is everybody semi-decent with that?
Yeah.
Okay. Now, if I gave you E to the stuff, that's much easier because the aux equation looks exactly like the DE. Just order replaced with degree. So then what's my DE look like? Yeah, y
Why
double prime.
X?
Yeah, x squared plus,
X, Y, prime.
yeah, 1xy prime minus 4y. I like it. So we do the process. Let's see what happens. I'm hoping at least a few of you guys are curious. And some of you guys are like, I just go with whatever the shit you put up there, man.
There's no choice.
You want me to want to do it also? What the hell's that shit?
It's a dictatorship.
Some of you guys might realize the nature of Cauchy-Euler and how it plays with those. And, some of you are like, well, once you start doing it, you'll see. It's exactly filling in. That's the whole idea. What we started with Cauchy-Euler was, as I took derivatives, it filled in what I lost. And now you can see that happening very directly. You're like, what are you trying to say? Can I just go ahead and, bring the x squared in? Very cool. Let's see. Just don't leave anything away. Plus minus yeah, so they're already like terms on the inside. The only thing I still have to take care of is,
Take out terms.
yeah, so who do I take terms out from?
I mean, just do one.
So I leave this guy alone.
1 and 0.
This guy becomes, the first term is
CN.
C1, x, and then that'll be starting at 2 now. And then this guy got to take
2.
2 terms out of. And remember that negative is applying to both of those terms. Right? It's minus this, so everything's negative inside. So that'll be minus 4C0. And then minus 4C1 x. And then what I have left starts at 2 now. Still the same definition on the inside. Okay. Let me go ahead and rewrite this here. So let's collect stuff together here. Let's get all the shucked stuff over here. Do I have like terms amongst the shucked stuff? I just like to say that. Shucked. So I guess negative 4C0 minus 3C1x, I like it. And then I can combine all those, the summation stuff. So n minus 1 cn plus n cn minus, where'd you go, 4 cn x to the n. Okay. That wasn't creepy at all, Jack. All right. The most annoying thing about these problems is there's so many n's running all over the place. You'll very easily lose an n, or your I will go here, and you'll put a +1 where it's not supposed to be. Mm-hmm. So as always, I try to grade based on understanding. So do you know the process and how it works? And if you make a mistake like that, I just continue grading from that point. You might lose something for that, and then did you do it right from there on out? So what can I say right here?
C0 equals 0.
C0 equals 0.
C1 equals 0.
C1 equals 0. That doesn't look promising, but let's see.
Or,
Don't worry, that recursion relation can skip terms and so forth, so let's see what happens. Right? I mean, that's what this says, isn't it? All right, let me see. Take the one that's working the best here. So what's my recursion relation? Let's see. See how everything's the same? So actually I get like n times n minus 1 plus n minus 4 Cn equals 0. Yep, okay. So I get Cn equals, well not Cn equals, got it. I get n squared minus n plus n minus 4 times Cn equals 0. I get n squared minus 4 times Cn equals 0. So either Cn is 0 or n squared minus 4 equals 0. Yeah, what did I do to us? Oh yeah, I kind of screwed us up, but that's all right. So I get n equals
plus or minus 2.
plus or minus 2. Now, now of course I had to make something without thinking all the way through. Well, actually, is this all right? Yes, it's fine. Okay. Now, this is a little bit sticky. That's why they didn't put one of these problems in here. But at least I wanted to on the basis of curiosity, right? We know the answer to this should be only one term has an actual value here. So this is kind of like saying for those terms, that's the only valid ends, which is weird. This guy right here kind of throws everything off because of the negative power. Because power series are supposed to not have negative power. So, I mean, that's something I should have thought of. I should have made it a 3 or something. Oh, well, too bad for me. But can you at least see how this makes some sense? It's the only way that I could have all the CNs be 0 except for those two. And we have to kind of allow for n to be negative for this to kind of work. Right? That is freakadelic. So so what does this mean? That means that C2 doesn't have to be 0. Because this is 0 at 2. And C negative 2 doesn't have to be 0 because this is 0 at negative 2. Do you guys see that?
Yeah.
There you go. So then that would actually capture, this would be the coefficient of x squared, and this would be the coefficient, you put little quotes around it. It's a little bit wonky, but it's the trouble Jeff gets into when he just makes something on the fly. On the surface, do you guys see why I wanted to look at that? And that's something that I would hope somebody would kind of think of and try to just do, just because you're like, oh, I'm curious, what the hell? All right, so that's what happens. That's what happens when you have an infinite number constant 0. That kind of weirdness happens to pick out the constants that are not 0. That's what has to happen. I like it. Maybe. Okay. Is that cool for 6.2? Do you guys want to see anything else from 6.2? I want to point out that nowhere in the instructions for 6.2, they do tell you in the problems 3 through 6, they say compare the series solutions with the solutions of the differential equations obtained using the methods of 4.3, right? Because all of those are constant coefficients, right? Try to explain the difference between the two forms of the solutions. So that's the easy step about we know what the answer should be, compare it to what we got, and then try to see, compare, in between the comparison you should see what's different, right? And that would really just be what we saw the other day. We saw the fractions reduced. And trying to fill it back in is the weird part. Well, what reduced? We have to work backwards. And that gets a little bit gross. That's the only section where they say anything related to that. Everything else is purely like the answer we got before, where you write out the first few coefficients that you got, the constants. Okay. All right, so that's 620. All right, so so we stay on track. I can't make. We have to talk about Laplace transforms, but 6.3 is actually semi-optional already. So 6.3, I'm going to make it extra credit. I will talk a little bit about it. 6.3 deals with singular points. And one reason why I'm okay with skipping this section is because there's a lot that this section doesn't show you.
What was the next one, 6.5?
Huh? No, the next one is chapter 7. There's a lot that this section does not show you in the derivation of the process. So if you want to look through it, if you look on page 254 at the bottom, you can see how they have to adjust the form of the solution to make it okay at that singular point. So tell me, what's the simplest way to have a singular point? Is that example we had earlier, like if I had something like this, if I just had right, I'd have two singular points.
When x is 0, because of the denominator, this is, I don't know.
Yeah, because the denominator is 0 at 2 and -2, then those are the singular points of this. And if you look at the way you have to adjust, I can't assume the form of the answer to be this now. I have to adjust it. How do I want to say this? Yeah, okay. I have to adjust it out front by a couple powers of x, just to kind of lift it. And actually, this would be around 2 and -2. Let me do that. Around 2. Let's say around 2. I'd have to adjust it by a couple. Oops. In this case, I think it would be just 1. But they put a little r there. That r is part of what you have to figure out what the required power is. And this little thing is a little adjustment for, if I multiply this whole thing by x minus 2, that sort of alleviates the problem at 2, doesn't it? If you ignore that it's going to be here. So I'm kind of like using this as an adjustment. I figure out what the r is based on